The paradox at the heart of mathematics. Consider the following sentence. This statement is false. Is that true? If so, that would make the statement false. But if the false, then the statement is true. By referring this back directly, these statements create an unresolved paradox. So if that's not true and it's not false, what is it? This question might seem like a slight thought experiment, but in early 20th century, it led Australian logist Cook Dogger to discovery that would change mathematics forever. Google discoveries has to do with the limitation of a mathematical proof. A proof is a logical argument that demonstrates why a statement about number is true. The building block of these arguments are called axioms, undeniable statements about the numbers involved. Every system builds on mathematics, but the more complex through to base arithmetic is constructed from axiom. In a statement about number is true, the mathematician could be able to comfort them with an axiomatic proof. Since ancient Greek mathematicians used this system to prove or disprove mathematical claims with total certainty, but when Google entered the field, some newly uncovered logical paradoxes were threatening that certainty. Primary mathematics were eager to prove that mathematics has no contradictions. Prover himself wasn't so sure, and he was even less confident that mathematics was the right tool to investigate this problem. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. A mathematical statement is simply true or false, but Google had no idea. First, he translates mathematical strings and equations into code numbers, so that complex mathematical idea would be expressed in a single number. This meant the mathematical statements returned those numbers were also expressing something about the encoding statements of mathematics. In this way, decoding allowed mathematics to talk about itself. Through this method, he was able to write, "These statements cannot be proved," as an equation, creating first self-referential mathematical statement. However, unlike the ambiguous sentence that inspired him, mathematical statements must be true or false. So, which is? If the false, that means the statement doesn't have a proof. But if the mathematical statement has a proof, then it must be true. This contradiction means that Google's statements can be false, and therefore it must be true that these statements cannot be proved. Yet this result is more surprisingly because this means we now have a true equation of mathematics that asserts it can be proved. This revelation at the heart of Google's incompleteness bureau, which introduced an entirely new class of mathematical statement. In Google paradigm, statements still are either true or false. But the true statements can be either be provable or unprovable within the given set of axioms. Furthermore, Google argued these unprovably true sentences exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics because there will always be true statements we cannot prove. Even we can account for these unprovable statements by adding them a new axioms to a large mathematical system. That very process introduces a new, unprobably true statement. No matter how many axioms you add, there will always be unprobably true statements in your system. It's Google's all the way down. This revelation rocked the foundation of the field, crushing those dreams that every mathematical claim will be one day be proven or disproven. While most mathematicians accept this new reality, some probably debated it. Others still try to ignore it and normally uncover the hole in the heart of their field. But as more classical problems were proven to be unprobably true, some began to worry this life's work would be impossible to complete. Still, Google's doors opens as many doors as closed. Knowledge of improbably true statements inspired the key innovation in really computer, and today some mathematicians dedicate their careers to identify probably and unprobably statements. So while mathematics may have lots of certainty, thanks to Google, they can embrace the unknown at the heart of any question for truth. What more? Consider the following sentence. This statement is false. Is that true? If so, that would make the statement false. But if it is false, then the statement is true. By referring to itself directly, these statements create an unresolved paradox. So if it is not true and is not false, what is it? This question might seem likely since but in the early 20th century, it led Australian logician Cook Google to discovery that would change mathematics forever. Google discoveries have to do with the limitation of mathematical proof. A proof is a logical argument that demonstrates why statements about a number is true. The building block of these arguments are called axioms, undeniable statements about the numbers involved. Every system built on mathematics, from the most complex proof to basic arithmetic, is constructed from axioms. And if the statement about numbers is true, mathematicians should be able to confirm it with an axiomatic proof. Since ancient Greek mathematics used this system to prove or disprove mathematical claims with total certainty, but Google entered the field, some newly uncovered logical paradoxes were threatening that certainty. Permanent mathematicians were eager to prove that mathematics has no contradictions. Google himself wasn't so sure, and he was even less confident that mathematics was the right tool to investigate this problem. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. A mathematical statement is simply true or false, but Google had an idea. First, he translated mathematical statements and equations into code numbers, so that complex mathematical idea could be expressed in a single number. This meant the mathematical statements written to these two numbers were also expressing something about the encoding statements of mathematics. In this way, the coding allowed mathematics to talk about itself. Through these methods, he was able to write, "These statements cannot be proved," as an equation, creating first self-referential mathematical statement. However, unlike the ambiguous sentence that inspired him, mathematical statements must be true or false. So, which is it? If it's false, that means the statements don't have a proof. But if the mathematical statement has a proof, then it must be true. This contradiction means that Google's statements cannot be false, and therefore it must be true that these statements cannot be proved. Yet this result is even more surprisingly, because it means that we now have a true equation of mathematics that in theory it can be proved. This revelation is at the heart of Google's incomplete theory, which introduced an entirely new class of mathematical statements. In Google's paradigm, statements still are either true or false, but the true statements can either be provable or unprovable within a given set of axioms. Furthermore, Google argued these unprovable true sentences exist in every axiomatic system. This makes it impossible to create a perfect complex system using mathematics because there will always be true statements we cannot prove. Even if you can prove these improbable statements by adding them as new axioms to a large mathematical system, that very process introduces a new, improbable true statements. No matter how many axioms you add, there will always be improbable true statements in your system. It's Google's all the way down. This revelation locked the foundation of the field, crushing those who dreamed that every mathematical claim will be one day proven or disproven. While most mathematicians accept this new reality, some fervently debate it. Others still try to ignore the newly uncovered hole in the heart of their field. But as more complex problems were proving to be improbably true, some began to worry their life's work would be impossible to complete. Still, Google's theorem opens as many doors as it closed. Knowledge of improbably true statements inspired the key innovation in early computers, And today, some mathematicians dedicate their careers to identifying provable and unprovable statements. So while the mathematics may allow us some certainty, thanks to Google, they can embrace the unknown at the heart of any equation for truth.